At assigned binary arithmetic, we need to have signs because in any number system, we are about to have positive and negative numbers. And as we already know, in the decimal number system, the plus sign is used to indicate a positive number when appended before that number, and a negative sign or a minus sign indicates a negative number. So, but in the binary system, the plus and or minus sign cannot be used because the system has only two symbols, and therefore the sign of a binary number has to be indicated using other bits like zeros and ones. There are three schemes actually for representing signed binary numbers. The first one is called sign magnitude, the next one is called ones complement, and the last one is called twos complement. So as an introduction, we have seen that if you want to add 7 plus 7, you can perform that very easily using the binary because you just need to find the number 7 as it is expressed in binary numbers and another number 7. You add them using the unsigned binary addition and perform that. But so far from what we have learned, assume we find an answer that says it is minus 7 plus 2. The number that you get after you perform this subtraction or addition, it needs to be expressed as minus 5, introducing a 1 before the number itself. Because this is number 5, we need to introduce a 1 for us to represent this negative sign. This is not a very friendly way, and as we already saw, the computers that use the binary number system find this quite unfriendly. So we need to come up with a very good and clear way in which we can represent signed binary numbers. So we start with the one that is referred to as sign magnitude scheme. And in the sign magnitude scheme, it's what I may have alluded to in the previous slide. The most significant bit, or the MSB, in the binary number is used to indicate the sign, while the rest of the sequences of binary digits are used to represent the magnitude. And therefore, you might say we know 5 is represented as 101. Then we might give ourselves a 7-bit scheme or an 8-bit scheme. We say that the 8th most significant digit is used to represent the sign of the number. So when we find a 1, this may represent a negative number, and we find a 0, this is used to represent a positive number. So if it is a number 5, you append zeros before it so that it forms 7 digits plus 1. Therefore, this is called an 8-bit scheme. In a similar manner, this is equivalent to number minus 5 because it has a 1 appended before the other numbers or the other digits that are representing magnitude of 5. So if we find 0, 0, 0, 0, the leftmost or most significant bit is 0, and then 0, 1, 0, 1. This is equivalent to positive 5 under the signed magnitude scheme. So we say a positive number has binary 0 for the most significant bit, whereas the most significant bit for a negative number is indicated by binary 1. And for example, we have a 9, it may be positive or it may be negative, and these 4 digits represent decimal 9, and this most significant bit is representing that it is a positive 9. In a similar manner, the 4 digits represent 9, but this represents a negative sign. Under the sign magnitude scheme, we say that the largest 8-bit number is represented by all ones except the 8th or the most significant bit being 0, and this is equivalent to positive 127, which is a very small number compared to the magnitude of possible numbers that you can find in a digital system. And the lowest 8-bit number in this scheme is all ones, which represents negative 127. The less significant bits from the 7th one to the 0th one, when you perform this binary conversion from binary to decimal, you find that this is number 127, but the sign is represented by a 1 as the most significant bit. So one inconsistency in this scheme is found when you want to represent a zero. So a zero in decimal may be expressed as is the same thing whether it's positive or negative. So if you are given a decimal number with a positive 0 or negative 0, this means the same thing. But if you wanted to convert them in the binary number system, you would find that positive 0 has its own version of representation, because we are saying the most significant bit is positive or is 0 for a positive and 1 for a negative. So this system doesn't know whether when we have a 0, that whether you put a positive or negative sign represented by a 1 or a 0, they are different. And therefore what you'll find is that we have a dual representation of zeros, because when you find 1 0 0 0 0, and when you cannot say that it is equals to 0 0 0 0 0, because these two things mean different things, and therefore we find the dual representation being unpreferable when you use the signed magnitude scheme. So this is an obvious disadvantage to have two distinct representation of a zero, because in an arithmetic process we don't want to find such inconsistency. And we say that the arithmetic rules for sign magnitude are therefore not as simple, or they become a little complex, and therefore the signed magnitude scheme is very unpopular, or it is rarely used in computer system because of such simple issue of representing zero that is signed.